You look up on a completely clear night, and what you see is, for the most part, darkness. Now, think about what science tells us about that same sky. Billions of galaxies, each one with hundreds of billions of stars. A number so absurd that no human mind can truly grasp it in its entirety. If the universe is so full of light, why is the night dominated by darkness? This question seems simple, but it has hidden one of the most elegant mysteries in all of astronomy for more than 300 years. And the final answer only came in the 20th century when we understood that the universe itself was not what we imagined. Neither eternal, nor static, nor infinite the way we thought. Today we're going to take this contradiction apart piece by piece, and in the end, you'll look at the dark sky in a completely different way. Start with the basics. On a clear night, you can see maybe 2,000 or 3,000 stars with the naked eye. It seems like a lot, but compare that to the amount of empty space around each one of them. Darkness dominates the sky. Stars are the exception, not the rule. And that's strange because the universe is immense. The most conservative estimates put the number at hundreds of billions of galaxies, just in the part we can observe. And that's just the slice whose light has had time to reach us. The rest, if there is even a limit, could be even bigger. Here's the reasoning that intrigued thinkers of the past. If the universe has stars scattered in all directions, without end, then any straight line you draw from your eyes pointing to any spot in the sky should eventually hit the surface of some star. No matter where you look, sooner or later, your line of sight would hit a wall of light. If that were true, there would be no real night. The entire sky should shine with the intensity of the surface of an average star, in all directions, all the time. There wouldn't be dark gaps between the points of light. There would only be light, uninterrupted, in any direction you looked. But that's not what we see. The night sky is mostly black. The stars appear as isolated points against a background with almost no light at all. Something in this seemingly logical reasoning is wrong, and finding exactly where the mistake was led humanity to rethink its very idea of what the universe is. Before we get there, though, it's worth understanding why the day on Earth is bright, because the answer to that smaller question is the first building block of the bigger answer. The simplest explanation for day is that the Earth rotates, and the side facing the sun is illuminated. But that alone doesn't explain everything. If sunlight were just a direct beam, it would only illuminate what it hit directly. The shadows would have hard defined edges. The rest of the sky would remain dark, and the sun would look like a bright disk surrounded by black, even at noon. But the daytime sky isn't like that. It's uniformly blue from horizon to horizon, even in the direction opposite to the sun. This happens because of the atmosphere, the thin layer of gases that surrounds the planet. When sunlight passes through this layer, it collides with air molecules and is scattered in all directions, a phenomenon called Rayleigh scattering. And this scattering is not the same for all colors. Shorter wavelengths on the blue side of the spectrum are scattered much more intensely than longer wavelengths on the red side. That's why when you look at any point in the sky, even far from the sun, you're seeing redirected sunlight, predominantly blue, coming from the entire column of air above you. The same principle explains the sunset. When the sun is low on the horizon, its light has to pass through a much longer path of air before reaching your eyes, sometimes 20 or 30 times longer than at noon. Along this long path, almost all the blue has already been scattered in other directions, leaving only the orange and red tones. And it's precisely because of the same atmosphere that, at night, the sky goes dark. The air molecules are still there, with the same ability to scatter light, but there's no more sunlight coming in to be scattered. The air becomes, for all practical purposes, transparent, and the only light that reaches you from any direction is the one that comes from beyond the atmosphere, from distant stars, from the moon, or from nothing. In other words, the dark sky we see at night is not an illusion created by our atmosphere. It's exactly the opposite. It's our atmosphere getting out of the way. It's the window opening. And what we see through it is the very face of the universe, unfiltered. If you took away Earth's atmosphere, the day would also turn black, just like it does on the moon. An astronaut standing on the lunar surface, under full sunlight, sees the ground shining intensely and the sky above him completely black. Without air to scatter the light, there is no ambient glow. There is no smooth transition between light and shadow. There is only direct light and absolute shadow, with no in-between. Each planet, depending on the atmosphere it has, writes its own version of the story. On Mercury, with practically no air at all, the sky at noon is absolute darkness, with the sun hanging in it like a blinding disk. No gradient, no transition, no color. On Mars, a thin atmosphere full of suspended dust creates a daytime sky in a beige and yellowish tone, almost like dusty caramel. And due to a curious physical inversion, Martian sunsets tend to be blue, exactly the opposite of what we see here. And on Venus, under a dense, oppressive atmosphere, about 90 times heavier than ours, sunlight is scattered hundreds of times before reaching the ground. The result is a suffocating yellow-orange sky where the sun itself loses its contours and becomes just a diffuse glow with no defined shape. An observer on each of these worlds might naively think they're seeing the universe as it truly is, but they would be mistaken. The brightness and color of the sky in any of these places only relate to the local air, not to what exists beyond it. To know what the universe really looks like, you need to look when the atmosphere isn't in the way. And that's what night on Earth offers us. Maybe you've noticed something strange in the photos that space probes take of other planets. The background is always completely black, without a single visible star. This often raises questions. If the universe is full of stars in every direction, why don't the cameras capture any of them? The answer has nothing to do with the universe being empty. It has to do with photography. Every camera needs to choose an exposure time. How long does the sensor collect light before generating the image? A planet like Saturn is extremely bright. So, photographing it well requires a short exposure that preserves the details of the rings and clouds without blowing the image out to white. The problem is that in a short exposure like this, the background stars, which are thousands of times fainter than the planet, simply don't leave enough signal on the sensor. They stay below the camera's detection limit. The same goes for the historic photos of the astronauts on the moon. They were taking pictures in broad lunar daylight with the ground and the spacesuits reflecting sunlight intensely. The cameras were adjusted for that brightness, and the stars, which are much dimmer, never had a chance to appear on the film. This is not evidence of fraud. It's exactly what any photographer would expect, given the equipment and the conditions. When instead we point sensitive instruments at any patch of the sky without any bright object in the foreground and leave the shutter open for much longer, the result changes completely. These long exposure images reveal entire fields filled with galaxies. A tiny patch of sky the size of a fingernail seen at arm's length can contain tens of thousands of them. The same principle appears in photos taken from the International Space Station. When the exposure is long enough and the camera is pointed at the night side of the Earth, with no bright planet interfering with the frame, the Milky Way appears in all its splendor, arching across the sky. The same band that, from the surface, is almost always erased by the light pollution from cities. The universe, when photographed the right way, is far from empty. The blackened photos of planets is a technical choice made by engineers, not a description of what really exists out there. And that only makes our original question even sharper. If there's so much out there, why does the sky we see with the naked eye remain so dark? This contradiction isn't new. Thinkers have been discussing it since the 17th century. The idea that in an infinite, static, and eternal universe, filled with stars distributed more or less uniformly, the entire sky should shine like the surface of a star. The geometric reasoning is simple to follow. Imagine concentric layers of space around you, like onion skins. A layer twice as far away has about 4 times more volume, and therefore 4 times more stars. But each star in that more distant layer also appears 4 times dimmer, because brightness falls off with the square of the distance. The two things cancel each other out exactly. That is, each layer, no matter how distant, contributes the same total amount of light. There are infinite layers like this, one after another, and the mathematical result is a sum that keeps growing without stopping. An infinitely bright sky with no darkness left anywhere. There's a classic analogy to really feel this firsthand. Imagine yourself in the middle of a huge, uniform forest, with similarly sized trees spread out everywhere. No matter which direction you look between the trunks, sooner or later, your view will be blocked by a tree. You never see a clear gap all the way to the horizon. A forest like this, dense and endless, wouldn't have clearings in the middle of the vegetation. Just like an eternal and infinite universe of stars shouldn't have dark patches in the sky. Names like Johannes Kepler had already stumbled upon this question centuries before, when he realized that an infinite sky, uniformly filled with stars, simply didn't match the darkness anyone could see with the naked eye. Other thinkers of the time raised the same question, each in their own way, without being able to solve the problem. This problem became known by its most famous name in the early 19th century, when the German astronomer Heinrich Wilhelm Olbers gave it a detailed mathematical treatment. Since then, it has been called Olbers' paradox, even though he was not the first to notice it. For almost a century, the paradox was treated as a logical curiosity, something that could be solved with some clever adjustment to the theory, without needing to abandon the idea of an eternal and static universe. The first attempt was to suppose that there was dust and gas between the stars, absorbing the light from the most distant ones before it reached us, a kind of cosmic fog hiding the excess brightness. But this idea runs into a simple law of physics. Energy does not disappear. If this dust absorbed enough light to block out the entire sky of stars, it would heat up until it reached thermal equilibrium and would start to shine just as brightly as the stars it was blocking. The problem wouldn't disappear, it would just change its source. A second attempt suggested that maybe the number of stars was, in practice, finite, or organized in a hierarchical way, in clusters within clusters, increasingly spaced apart, so that the total sum of light would never diverge. But modern observations don't confirm any of that. The deeper telescopes look, the more galaxies they find, not fewer. On large scales, the distribution of matter in the universe is remarkably uniform, with no sign that the density of stars decreases as we look farther away. Each of these attempts had something in common. All of them tried to preserve the idea of an eternal and mutable cosmos, just adding some extra ingredient. And no extra ingredient really solved the problem. The lesson, even though no one wanted to admit it right away, was something else. The very foundation was wrong. The universe couldn't be both eternal and static at the same time. The definitive resolution came at the beginning of the 20th century with a discovery that changed everything. The universe has an age. It began at some point about 13 billion and 800 million years ago, and since then it has been expanding and cooling. This single piece of information is already enough to dismantle the paradox at its root. The original geometric argument implicitly assumed that the light from any star, no matter how distant, would have already had plenty of time to reach us. In an eternal universe, this would be automatic. Infinite time and infinite opportunity for the light to complete its journey. But if the universe has a finite age, that's no longer true. The light from a star 1 light-year away takes a year to arrive. The light from a galaxy 10 billion light-years away takes 10 billion years. And there are regions so distant that the light coming from them, even traveling at the maximum possible speed, still hasn't had time to reach us. It's simply still on its way. And there's something even deeper here. Looking into the distance is looking into the past. The light that reaches your eyes from a distant galaxy left there billions of years ago. If you look deep enough, you reach a point where you're seeing a moment before the very existence of stars. A time when the universe was still a hot gas soup without any starlight to emit. In other words, the most distant regions of the sky aren't empty spaces waiting to be filled by stars. They are windows into the youth of the cosmos itself, a time when there simply weren't any stars there to shine. That's why the infinite sum of light is never completed. The most distant layers, which in the old theory should contribute more light, in practice contribute nothing. We call this slice of the universe, whose light has had time to reach us, the observable universe. It is defined by a horizon, a limit determined by the maximum speed of light in the age of the cosmos. Beyond it, there may even be more universe, full of galaxies and stars, but no light from there has reached us yet. But the age of the universe is only half of the answer. The other half has to do with an even stranger fact. Space doesn't stay still, it stretches. The distance between two distant galaxies increases over time, not because they are flying away from each other through fixed space, but because the very fabric of space between them is expanding. It's the expansion of the universe, one of the most well-confirmed facts in all of modern cosmology. This has a direct consequence on light. When a photon travels through space that is expanding, its wavelength stretches along with it. The longer the journey, the stronger this stretching, a phenomenon called cosmological redshift. For extremely distant sources, this shift is so intense that light which started out as visible light reaches us already shifted to the infrared, to microwaves, or to even longer wavelengths. The energy still arrives, but outside the narrow range that our eyes can see. So even photons that have technically completed the journey often arrive invisible to us. And there is a final layer of darkness, even more absolute. The expansion of the universe is accelerating, driven by something scientists call dark energy, whose exact nature is still an open mystery. Because of this acceleration, there is a cosmic event horizon, a boundary beyond which the light emitted today will never be able to reach us. Because the space between us and the source is growing faster than light can travel through it. This means that there are directions in the sky whose contents are and always will be permanently out of our reach. Not because of lack of time, but because space itself is receding faster than any signal could travel through it. Add all of this up. A young universe whose most distant light is still on its way. Expanding space that pushes the incoming light out of the visible spectrum. And an acceleration that makes part of the cosmos permanently inaccessible. The natural result of these three things together is exactly the sky we see. Dark, dotted, silent. There is direct and visible evidence of this story, the cosmic microwave background radiation. It is the oldest light that any human instrument has ever detected, an echo that originated when the universe was only 380,000 years old, a blink of an eye compared to its current age. At that moment, the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms. And for the first time, light was able to travel freely through space without being constantly absorbed and re-emitted by the hot plasma that had filled everything until then. At that moment, the entire universe glowed in all directions, with the orange glow of a hot stellar surface at nearly 3,000 degrees. But since then, space has expanded by a factor of more than 1,000, and that light, along with it, has been stretched in the same proportion. What was originally a hot, visible glow reaches us today as a cold whisper of microwaves, just 2.7 degrees above absolute zero. If our eyes could see microwaves, the entire sky, in all directions, would be evenly lit, without a single dark spot. In other words, the sky that seems empty to our eyes is not empty at all. It is overflowing with light, just in a color that our biology was never built to see. And microwaves are just one band among many. In the infrared, the sky is filled with cool stars, brown dwarfs, and reheated dust clouds, including the same dark bands that cut across the Milky Way in visible light photos, which appear bright and full of structure when seen at this wavelength. In X-rays, the skies become a map of cosmic violence. Disks of matter being devoured by black holes, neutron stars with surfaces at millions of degrees, and the hot gas that fills entire clusters of galaxies. In gamma rays, we witness the most extreme events that exist. The collapse of massive stars into supernovas, the merging of neutron stars, explosions so energetic that for a few seconds they outshine entire galaxies. In radio waves, we hear pulsars spinning like cosmic lighthouses. The whisper of cold hydrogen spread between galaxies and the jets of plasma launched by supermassive black holes at distances of hundreds of thousands of light years. And beyond light, the universe still speaks through entirely different channels. Through neutrinos, almost ghost-like particles born in the hearts of stars, and in supernova explosions, and in gravitational waves. Ripples in the very fabric of space-time produced when extremely massive objects collide. Each new band we learn to detect has revealed entire populations of objects that no previous instrument could perceive. The universe, it seems, doesn't reveal everything all at once. It waits patiently for us to build the right receiver to hear each new message. Put all these threads together, and the darkness of the sky stops seeming mysterious and starts to look simply like the natural result of how the universe is made. Daylight is the work of our atmosphere, not a sample of the cosmos beyond it. The black background in photos of other planets is a matter of exposure, not proof of emptiness. And the darkness between the stars in the end is made of age, of expansion, and of horizons, regions whose light has not yet arrived. Light that has arrived but was stretched beyond our visual reach, and regions that, because of the acceleration of space, will never reach us. There is also a final ingredient, perhaps the most humble of all. Our own eyes can only see a very narrow slice of the entire electromagnetic spectrum that the universe produces. An observer sensitive to microwaves would see the entire sky shining uniformly. An observer sensitive to X-rays would see intense points where black holes are feeding. The darkness we see is, in part, a feature of our biology, not just of the cosmos. And yet, this darkness is not a flaw, nor emptiness, nor an accident. It's a message written in the only language the universe had available to communicate with us, without us needing to travel there. That it had a beginning, that space keeps stretching, and that there are boundaries we will never cross. The next time you look up on a clear night and see that black background between the points of light, remember, that's not absence. It's the fingerprint of a young, expanding universe, told in a language our eyes can only half read. But even so, it was enough to reveal to us some of the deepest secrets of everything that exists.